move on to the next one. All right, this says calculate the osmolarity of the following solutions. So first off, before we even begin, I'm going to write out what osmolarity is. Osmolarity equals number of particles per liter of solution. That's osmolarity. So we need to keep that in mind as we go to calculate these things. Remember when I was talking about osmolarity, you just need to ask yourself if you have a compound in your solution given in your problem that will dissolve into ions or not. Okay, we would consider those ions to be particles compared to the molecules. Sometimes you'll have a compound, if it's an ionic compound especially, that will dissolve into particles, and then you need to know how many different particles, how many different kinds of ions would you get from one molecule. And then sometimes you'll have a molecule that's more of a covalently bonded molecule that will not dissolve into ions in solution. For example, glucose will not dissolve into ions. Okay, so you see we have glucose and sucrose. Those kinds of molecules, they are the particle. That's the smallest unit we can get. So we'll keep that in mind as we go forward. I'm going to zoom in to kind of give myself some more space here. Or at least I'll maybe write smaller this way. So if I have one molecule of NaCl, I will get I'll get one sodium cation and I'll get one chloride anion. So if I have one molecule of NaCl, I'll get one cation and one anion. That's two particles, right? Another way you can write this out is if I have 0.3 molar NaCl, that is 0.3 moles of NaCl per liter. Molarity is moles per liter. And if I break this up into its ions, what I'll end up with is 0.3 moles of sodium cations per liter plus 0.3 moles of chloride anions per liter. And now, knowing that, we just add these two things up. These are our particles, okay? So we've got to add up the total amount of particles we have here, moles of particles, which is 0.6 moles of particles per liter. And I think I need to change my definition. I forgot a word in my definition, I'm realizing. It's not necessarily numbers of particles. It's moles of particles. That is osmolarity. So for problem number 1, we have 0.6 moles of particles per liter, which is 0.6 osmoles. Okay. Okay, now let's do number 2. So I'm going to zoom in so that I can write small again. With glucose, I'm going to just write this out. If I have 0.5 molar, I have 0.5 moles. Let me erase this line. I'm going to say capital G for glucose per liter. And that equals, glucose is the smallest particle we can get here. Glucose does not break apart into ions, so we don't have any smaller particles it will dissolve into. So what I have is 0.5 moles of glucose particles. If it helps for you to see it like that. Okay, then if I have 0.1 molar NaCl, we'll do the same thing we did up in part 1, we just have a different molarity. So we would say plus 0.1 moles of Na plus, because that's one type of particle we'll get per liter, plus 0.1 moles of Cl minus particles. It's another type of particle the anion here will get. Now we add this up, 0.5 plus 0.1 plus 0.1 equals 0.7 moles of particles per liter, which is equal to 0.7 osmoles. Okay? So that's number 2. I'm probably going to need this line gone. Number 3, let's look at sucrose and calcium chloride. So if I have 0.2 molar sucrose, I have 0.2 moles of capital S sucrose particles. Sucrose is very similar to glucose. It's a different kind of sugar in that it will not dissolve into smaller particles in solution, okay, per liter. Now let's think about calcium chloride here. If I have 1 molecule of calcium chloride, I will get 1 calcium cation, and I will get 2 chloride anions, okay? So we're going to keep that in mind as we write out the osmolarity for this. So we'll say plus, if I have 0.1 molar calcium chloride, I'll have 0.1 moles per liter of calcium cations, plus, now because I'll get 2 anions out of every 1 molecule, I have to double the number of moles of chloride anions I would get here. So instead of 0.1 this time, it would be 0.2 moles of Cl minus particles per liter. Okay, and I got that from looking at this subscript 2 here that I'm circling. When there's a subscript 2, if one of these molecules dissolves, I'll get 1 calcium cation, 2 chloride anions. So when that happens, if I have 0.1 molar of this substance, I'll get 0.1 molar of the calcium cations and 0.1 molar, which is moles per liter, or sorry, 0.2 molar, which is moles per liter of the chloride anions. Now we're going to add all this up. 0.2 of the sucrose particles plus 0.1 the calcium particles and another 0.2 of the chloride particles. Total gives us 0.5 moles of particles per liter. Notice when we make this transition, we don't care about the identity of our particles anymore. The sucrose, the calcium, and the chloride, we're all just saying, these are all just particles now. Okay? In total, that is 0.5 osmoles. Okay? Lastly, let's look at sodium NaH2PO4. If I have 1 molecule of this, I will get 1 sodium cation, and I will get 1 H2PO4 minus anion. And this probably looks a little bit foreign to you guys, this right here, but I believe if you go look at your polyatomic chart, that anion might very well be on there. It's not one you had to memorize though, but it is the anion here with a -1 charge. So if we're looking at this compound, if we have 0.2 mole per liter of NaH2PO4, we will get 0.2 mole of sodium cations per liter plus 0.2 mole of the anion per liter. Now we just add those up. So total that equals 0.4 moles of particles per liter, which is 0.4 osmoles. Okay, so that was quite a bit, but that was some practice calculating osmolarity for exam 3. All right. I believe this problem, sodium thiosulfate. This is from chapter 9 material. Okay. So I actually want to look at, I believe there's some, sorry, looking something up. I believe the products for this reaction are not as straightforward as I make it look in this problem. And in fact, there might be some information missing that I realize we need. So I am going to get that for us really quick. Just give me one moment. I'm going to pause the recording and I'll start the next